What about the span of a set that contains only one vector? That's the set of all scalar multiples of that vector, which we saw earlier is the line through the origin and the point corresponding to that vector. It's a one-dimensional structure. What about the span of the empty set? We saw that this is just the origin. That's a zero-dimensional object. What about the span of two vectors? In this case, that gets you all the points in the plane. So it's a two-dimensional object. What about the span of three vectors? Similarly, that's a plane in 3 dimensions. It looks like this. A plane is a two-dimensional object. This raises the question, is the span of k vectors always a k-dimensional geometric object? The answer is no. For example, the span of the 0 vector consists just of the 0 vector. That's a zero-dimensional geometric object. The span of these two vectors is a line, which is a one-dimensional geometric object. The span of these 3 vectors is a two-dimensional object, a plane, which raises a fundamental question. Given k vectors, how can we predict the dimensionality of the geometric object that's formed by their span? So we've seen that the span of these 3 vectors forms a plane in 3 space. And in fact, this is useful for plotting the plane. So here I've taken multiple choices of alpha and beta and plotted what you get. So there's a more familiar representation of planes, which is this, the set of triples x, y, z, satisfying an equation of this form. Now, we can use vectors to represent the same equation. So the set of vectors x, y, z such that this dot product is equal to 0. So we're describing a set of vectors using a linear equation with the right-hand side of 0. We can similarly describe a line in 3 dimensions by using 2 equations with right-hand sides equal to 0. So it seems we have 2 ways to represent a geometric object, such as a line or a plane. We can represent it as the span of some vectors, or we can represent it as the solution set to a set of linear equations where the right-hand sides are 0. So we've got these 2 methods of representing things. One of the great themes of computer science is having multiple representations is very often useful. And we'll see it's true in this case as well. So here's a plane represented as the span of 2 vectors, and the same plane represented as the solution set to this linear equation with the right-hand side equal to 0. Here's an example of a line, and this line can be represented as the span of this single vector or as the solution set of these 2 linear equations with right-hand side equal to 0. Each of these representations has its uses. For example, suppose you have 2 lines and you want to find the plane that contains those 2 lines. Let's say the first line is the span of this set consisting of 1 vector. The second line is the span of another set consisting of another vector. How would you find the plane containing both of them? Well, it turns out it's the span of those 2 vectors. So this representation is convenient for finding the geometric object containing 2 smaller dimensional geometric objects. Now, suppose I want to find the intersection of 2 planes. Well, let's say I've represented one plane as the solution set of this linear equation. I've represented the other plane as the solution set of another linear equation. How can you find a representation of the line that is the intersection of these 2 planes? It turns out you want the points, the triples x, y, and z, that satisfy both these equations. So by using this representation, we can get the line that's the intersection of these 2 planes. what's common about these two representations for sets of vectors that form geometric objects? It's a subset of, in this case, r to the d, satisfying three properties. The first is the subset contains the zero vector. The second is if a subset contains some vector v, it contains every scalar multiple of that vector. And the third is if the subset contains two vectors u and v, it also contains their sum. So let's see why the span of a collection of vectors satisfies these three properties. The first one is easy. The span of vectors v1 through vn is the set of all linear combinations of those vectors. Here's one linear combination where you take every coefficient to be 0. That obviously gives you the zero vector. So property v1 is satisfied. What about property v2? Well, let's take any vector in the set, that is, a vector in the span, which is a vector that can be written as a linear combination of v1 through vn. So we have a vector that's written at some linear combination. You have some scalar alpha. Then the scalar vector product, alpha v, can be also written as a linear combination of those vectors v1 through vn. You just multiply all the coefficients by alpha. Now for property v3. Property v3 states that if two vectors u and v are in the span, then their sum is also in the span. So let's say u and v are in the span. That means that u can be written as a linear combination, and v can be written as another linear combination. Well then, we can represent their sum by just taking the linear combination where each coefficient is the sum of the corresponding coefficients in u and v. Now let's turn to the other representation, the solution set of a collection of linear equations where the right-hand sides are all 0. Now, property v1 is also easy. Take the 0 vector and plug it in. Well, a1 dotted with the 0 vector is 0. a2 dotted with the 0 vector is 0, and so on. All the dot products with the 0 vector are 0. So clearly, the 0 vector lies in this solution set. Now let's turn to v2. Take some vector that's in the solution set. That is, all these dot products are equal to 0. And now consider whether alpha times that vector also lies in the solution set. Well, what's the dot product? a1 dotted with alpha times v. That's the same as alpha times a1 dotted with v, which is alpha times 0, which is 0. So similarly, all these linear equations also hold of alpha v. So that proves property v2. Now let's turn to property v3. Similarly, suppose you have two vectors u and v that lie in the solution set. Well, that means u and v satisfy all these linear equations. That is, the dot products are all 0. a1 dot u is 0, and so on up to am dot u is 0. And similarly, a1 dot v is 0, all the way up to am dot v is 0. Well, then it's easy to see that the sum of u and v also lies in the solution set. Why is that? Let's look at the dot product. a1 dot u plus v is the same as a1 dot u plus a1 dot v by the distributive law. a1 dot u is 0, a1 dot v is 0, therefore their sum is also equal to 0. So this shows that all those equations also hold of the sum u plus v.